In this presentation, we're going to go over linear regression. And basically, I'm going to show you how to do linear regression using a spreadsheet. But I'm also going to teach you some of the backhand calculations associated with regression, as it's sort of been asked of me to kind of clarify what some of these equations are. So what is the actual purpose of conducting a linear regression? And the reason is that when we're in the engineering world, we model a lot, and modeling allows us to sort of forecast and make predictions about what how maybe a part's going to perform, or how maybe our systems are going to react. And linear regression allows us to build a certain type of model. And based on, in this case, linear regression is based off of the relationship between two different parameters. And the model here takes the form of a straight line. And that straight line basically is used to sort of best fit the data and give us something that we can model and use in the future. And then we can also go back and see how good that model actually is, essentially by calculating something like an r-squared value, which we will be doing today. And that tells us, this model is good up to a certain percentage. So a lot of you have probably done linear regression, or you've seen it before. Maybe you've gone into Excel and you've had a scatter plot and you've added a trend line and even computed an r-squared value. So today I'm actually going to show you what the sort of backhand calculations are, what the different equations are that actually make up a linear regression, and then we're going to go into Excel and actually compute it. When we conduct a linear regression, we actually do it to find the line that best models the relationship between two parameters. And so the equation we use for linear regression is y hat is equal to beta 1 x plus beta naught. So mathematically, you should recognize this equation, right? This is essentially just an equation for a line, where our b naught essentially is just the slope, and our our beta naught is equal to where our y value intercepts 0, or crosses the y-axis. So what we want to do when we're performing a linear regression is we want to choose beta 1 and beta naught such that the sum of the squared errors between the actual y values, so this y hat represents the model value for y. So what we want to do is we want the error between the actual values of y from our scatter plots and this modeled value of y, we want those errors to be as small as possible. So let's kind of go and look at that a little bit more in depth. So here we have some data, and this is some data we're actually going to play with in a minute, but it's cost per energy, and I'll kind of explain this data a little bit more. But I can tell you now, I can sort of better elaborate our y hat is equal to beta 1x plus beta naught equation a little bit better. So like I was saying earlier, what we want to do is we want to be able to choose b or beta 1 and beta naught such that the sum of the squared errors between this y hat and these actual y values for these points are as minimal as possible. So what does that actually mean? So at this point here, we have some distance between the y value for the actual point and then the y hat value. So where that line actually is. And this distance is called error. And we also call these residuals. And I'm actually going to refer to them as residuals for the remainder of this presentation. So basically what we want is we want the sum of the squared residuals to be as small as possible, and then that tells us what our beta 1 and our beta naught values are going to be. So what does that look like mathematically? And beta 1 is equal to the sum of xi minus x bar times yi minus y bar over the sum of xi minus x bar squared. And essentially what this is doing is it's sort of giving us a value based on, you know, calculating what those residual differences are. Now, when we go into Excel, there's a sort of nifty trick we can use in that the numerator and the denominator of the beta 1 equation are actually similar to other things we've come across before. So the numerator, up here, is actually equal to the covariance times n, our sample size. And the denominator is actually equal to the variance times n minus 1. So we can actually very simply go into Excel and use these commands and calculate this stuff instead of actually going in and painstakingly going in and sort of calculating what all of these individual pieces are and then summing them up. Beta 0 is equal to y bar minus beta 1 times x bar. And these values we can very easily calculate using the data we have. They're just the averages for the different parameters. So let's go into Excel and do this. So now we're in Excel, and you can see the data that we're using is energy and cost, and what we're trying to do with our linear regression is determine what the relationship is between them. And we have 12 different data points, so a different energy use and cost for each month of the year. So to calculate our beta 1 value, remember that the numerator was equal to the covariance times the sample size. So I'm just going to type in numerator here, and I'm going to type in covar and select our two data points, multiply it by our sample size, which is 12, and our numerator is equal to that. Our denominator is equal to the variance, but just of the x values. So in this case, that's our energy. And then we multiply that by n minus 1, which is 11. And so we get a beta 1 value equal to the numerator divided by the denominator, and that's our beta 1 value. Now, the next thing we need to do is we need to calculate x bar and y bar so that we can then go in and calculate our beta 0. So x bar is simply just the average of our x values. Oop. And y bar is just the average of our y values. And so our beta naught is equal to y bar minus beta 1 times x bar, and we get a beta naught of 13.56778. So our beta 1 and our beta 0 or beta naught are, these values represent the case where the residuals, the sum of the squares of the residuals, are as minimal as possible. So the nice thing is with Excel is that we can actually do this much easier, and what we can do is we can just graph it. So we can scatter plot our data, as you can see here, and I'm going to make a couple of quick adjustments so we can see it a little bit better. Ooh. Sorry, I wanted this to be 1,000. So here we have our data. What we can do is we can actually put a trend line in. So you select the data, right click, add trend line. In this case, we're just going to do a basic linear equation. And down here, we can say display equation on chart. So we're going to do that. And you can see by looking at our equation that we have in fact actually calculated correctly by doing our backhand calculations beta 1 and beta naught, which are displayed in this equation here, where this is beta 1 and this is our beta naught value.